Hi, everybody. So, yes, we're good. Okay. So let's get going. Let's check one thing. All right. I had more annoying Windows Mac rendering difficulties. I think I fixed them right before class, but if the slides you're looking at on your laptop look slightly weird, that's why. All right. So the motivating problem of the day. Today we're going to talk about a new topic called a concentration inequality. And our motivating problem is, imagine we want to do polling for an election. So maybe we want to know in the 2024 election, how many people are going to vote for Donald Trump, what fraction of people? And one approach which is used is to ask random people. And as long as we ask enough of the right people, who are the right people, the people that will vote, we'll get an accurate result. But the question is, how many people do we need to ask? So we could think of this polling question as a coin flipping question. So every person that we ask, like, are you going to vote for Donald Trump? What do you think? This is your question for you. Are you going to vote for Donald Trump in the coming election 1 year ago? You cannot vote. Okay, see, so you wouldn't count. How about you? No, okay. And so forth. I'll ask everybody. And everybody's basically a flip of a coin. In your case, it was like, I'm not eligible, right? So let's say heads is a Donald Trump vote. If 50.2% of the population will vote for Donald Trump, then in this model, this crude model of voting, then P equals 0.502. And I'll note that this coin flipping is not modeling something about like the randomness in your head. Like, it is true that for some people who are right on the fence, maybe like a shirt they see someone wearing on the way into the polling station or what they eat for breakfast or whatever will push them over the edge. I'm not thinking about that. I'm just imagining that it's the chance that like every person has a deterministic vote, and 0.502 is the fraction of people who are going to definitely vote for Donald Trump in this universe. So our goal then is to flip the coin a bunch of times to estimate the probability of heads. That's what we want to do. Okay? So let's suppose, inspired a little bit by last week's homework, that we flip a coin 10,000 times, let's just say. It could be this polling question, or it could be just an actual real coin. And we get heads 4,800 times and tails 5,200 times. Let's say P is the true chance of heads on the real coin, right? So that's not a random quantity. It's like a fact of the universe. And then P hat is our estimate. What should we use as P hat? Like, what's the best estimate of the probability of heads? 0.5. Well, why?
Just think about it for a moment.
We did an experiment.
Okay.
We got 4,800 heads.
Then 0.48, because that's like
The 0.48 seems like the best result here. Though you were bringing up an interesting question, like maybe I have some a priori knowledge, and that's a different way of thinking about probability. If you want to take into account like your priors for how fair coins are, then that's a separate philosophy. But here I'm being purely frequentist. I'm just saying, based on only this result, what's going to happen? And as you said, 0.48 makes sense. And this is similar to what you saw on homework 11, problem 4a. Okay? All right. How confident should we feel? That's not something we talked about on that homework problem. We said 0.48 is the best, but we never said how good it is, and that's going to be the topic of today. So how sure are we that we're off by, say, 0.01 or less? Okay, so what's the chance that the real P is in this range between 0.47 and 0.49? That's what I want to know. Another way of expressing that is to say, what is the probability that the difference between my estimate, 0.48, and the true probability P is less than or equal to 0.01. And I put an absolute value here because maybe we're a little under, maybe we're a little over. Okay? That's what we're going to try and solve today. All right. So what I can tell you is that today we're going to derive a specific bound called the Chebyshev bound, which will say that no matter what, as long as this coin flipping process I've described is actually, like that the coin actually has some probability of heads, the Chebyshev bound will tell us that the probability that we're off by 0.01 or less is going to be greater than or equal to 75%. Okay? I should really have a less than or equal to. It doesn't actually matter here, but sorry, minor line missing there. But in other words, we have at least a 75% chance of being right, where we define right by being within 0.01. Now, if I pick a different definition of right, like say 0.02 or 0.03 or whatever, then I'll get a different chance. And that's what we're going to be experimenting with. Now, I haven't told you where this came from, but I'm going to over the course of the day. Okay, so this is one way of thinking about it. So more generally, if we don't think about a specific 0.01, if we just pick an epsilon, like the amount we want to be off to be considered right, and we pick a confidence level C, the thing we're going to be trying to compute today is that. How far are we deviating from the true probability, and C is going to be our desired confidence level, which maybe it's 75%. Okay. All right. Any questions about this? All right. So I am not going to, later on, I'm going to tell you that, let's say we want to find what's the number of, so what we just showed before is for a given n, right? Like what's, like for 10,000, I told you that there's a 75% chance you're within 0.01, but the opposite question, which I didn't actually say out loud, but I had on the slide, is imagine it's the other way. Like I have a confidence level that I'm really curious about and an error that I want to be within, and now I want to say how many flips do I want to do? Why is that a useful question in the context of polling? Yeah?
So we know how many people we need to actually sample to get it.
Right, tells us how many people we need to sample. How many times do we need to flip the coin to have a certain confidence, right? Okay. So to achieve our goal, it turns out, and we'll prove this later, that if we flip 1 over 4 epsilon squared times 1 minus c times, that will be good enough. So I pick an epsilon, 0.01. I pick a c, 99%. And once I have those two choices, epsilon and c, that tells me the n I need, and I haven't proven that, but I want to play around with that first, and then we'll prove it later. Okay? So we're going to use something called Chebyshev's inequality, which we still have to derive and experiment with. But let's see what it means in terms of our motivating question. Okay, so already, as an example, let's say our confidence level is 99% rather than 75, and our epsilon is 0.05. Then the target n is going to be 1 over 4 times 0.05 squared times 0.01. Where'd this come from? That's 1 minus c. Okay, that's 10,000. Okay, so if you just plug these things in, you get 10,000. And c, again, is our desired confidence level. So if we flip our coin 10,000 times, there's only a 1% chance they're off by more than 0.05. Yes? This is related to hypothesis testing, but we'll talk about that maybe later. Yeah. Yeah.
If hypothetically we were doing it for like some small state legislator election where like only like 15,000 people are going to vote, is this not going to mess up our sample?
Right. So the question was, let's say that n starts being bigger than the number of voters, or close to. So if we're very close to the number of voters, so we'll see later. Actually, I'll defer that question for later. I'll come back to that. Okay, for now. So if we get, for example, that the probability, our estimate is 0.48, the bound says that the chance is less than 1%, then the true p lies outside of this range, which is 0.05 on either side. So I came up with 0.48, 0.05 less is 0.43, 0.05 bigger is 0.53. Okay, so that's what this Chebyshev bound will tell us. If we flip a coin 10,000 times, that's where we lie. Okay? Now there's a slightly different form, which is what's in the notes, and which makes this denominator nicer, which is instead of using c, our confidence level, we use 1 minus delta, and delta is our acceptable failure level. So if c is 99%, then delta is going to be 1%, 1 minus 99, and if you do that, then this denominator becomes delta. Okay, why am I doing that? Because that way I match the notes. C is a more natural quantity, I think, but 1 minus delta is because you get just a delta in the denominator, and also later the math works out slightly nicer, I'll use delta. Okay, so there's only, notice these two things are exactly the same, I just am using 1 minus c. Okay, all right. So here's the question. I'm going to observe that while it is true that 1 over 4 times 0.05 squared times 0.01 is 10,000, it is also true that 1 over 4 times 0.01 squared times 0.25 is equal to 10,000. What, like both of these things are true. I just changed up the denominator here a little. What does that tell me about p hat in terms of confidence levels and epsilons? If that makes sense. So this told us there's a something, and this tells us something else. Yeah?
Tells us that if we make epsilon smaller, then our confidence level is going to go down.
Right, yeah. So if we bring epsilon lower, we want a tighter bound over what the true p is. Like we want a more sense of how close we are. We're going to be less confident that we're really close. Okay? In other words, that's what we had before. There's a 75% chance. In this case, we can only say there's a greater than 75% chance that the true p is in the range 0.47 to 0.49. Okay? In other words, this equation tells us a whole family of things about the quality of our p hat. So I'm going to run a simulation. I just flipped a coin 10,000 times, and 4,978 times it came up heads. Okay, I'm going to do it again. That time, 5,070 times it came up heads. That time, 5,067, and so forth. Okay, so I just keep doing this over and over. You could do this later if you'd like. Okay, so this particular case, I got 4,925 heads. And what this bound tells me is the following. Really, I think I should have a greater than before each of these, greater than or equal to make it more clear. But what this tells me is that if I want to know what's the chance that I'm between, let's say, so the estimate I came up with was 0.492, then there is going to be a 75% chance that I lie, as I said before, within 0.01. Okay, that's what the Chebyshev bound tells us. It also tells us that there's a 99% chance that I'm in this wider range, or a 99.99% chance that I'm in this very wide range. Okay, that one should hopefully feel good. But if I want to know what's the chance that I'm like really close, then my chance is going to be lower. Okay, so it's what the Chebyshev bound gives you is a whole family of statements about the quality of your estimate. Okay, and in all these cases, it's saying that I have a greater than or equal to that percent chance of being right. Any questions about this? Okay. All right. So I haven't told you where the Chebyshev bound comes from, but I think the key thing that can be a little tricky when you're first seeing this is that it is telling you about the quality of your probability estimate in two dimensions, both how close you are to the answer and how confident you should feel about being that close. And you get all of these statements all in one. Okay? So all of them are true because of the Chebyshev bound. All right. So one surprising observation here, if we think about this, it says it doesn't matter how big the population of your voting populace is. The number of people we need to poll to get some desired degree of accuracy is constant, which seems very counterintuitive in some ways, right? Like if there's 10,000 people, there's only so many different opinions, right? But if you have like 1 billion people, like in a country like, say, China, there's going to be just much more diversity of opinion, right? Like if you're only asking 1,000 people, obviously you're going to be missing some, I don't know, religious sects or people that have some, off-kilter belief. But the idea is that if really truly that the voters are being drawn totally uniformly from the whole population, and you are also drawing totally uniformly from the whole population, it all works out, yeah. Yeah, exactly. Everything here is assuming uniformity. Yeah. Okay. So we asked 10,000 people, and our bound says we have a 99% chance of being within 0.05 of p. And that's true whether we're surveying a country with a small population or a small election or a giant country. But the framing only works because we're assuming this not true thing, which is that our sample is the true random sample among all of the voters. Okay? If you had that, if you were really sampling exactly the people who are going to vote, and you uniformly sampled them, and you know that all of them are going to vote, like you psychically know that these specific 3,970,000 Canadians are going to vote in this municipal or some state level election, and I know exactly who they are, and I sample them truly uniformly, and they all vote deterministically, this will work. And we'll come back at the very end of the lecture talking about why it is hard in practice, but that's the framing. If it doesn't seem believable, it's because the thing I've just described is impossible. But if you truly could be uniform, it would work out. Okay. All right. Now again, I've come up with this formula without any proof, no rationale. I just tried to show you what it means. And the reason I did that is because it is often challenging to understand what it even is. It's like a little fuzzy, like, okay, I'm going to come up with an estimate of a probability of heads. Already that's a little bit weird. And now I start saying, well, how good is it? Well, I can't tell you really good or bad or whatever. It's actually got this two-dimensional nature, delta and epsilon both. Okay? So what we're going to do to get this expression, now that we understand it hopefully, we're going to use something known as a concentration inequality ultimately to derive this expression. And it's a mathematical bound that some random variable, how likely it is that it can stray from some quantity. We observe, for example, that if we roll a bunch of dice, that the mean increases linearly with the number of dice we roll, but the standard deviation increases with the square root. So that sort of concentrates around its mean, that if I roll 100 dice, we start getting this sort of bell curvy looking thing. And the concentration inequality is going to be a very generic way of reasoning about how random variables can stray from their means in general. Okay? So when I say concentration, I mean like how close it is to some specific quantity. Okay? So an example that we're going to have here that we're going to work through is our first one is, let's say I have a non-negative random variable. Can't be negative. And let's say its expectation is 45. We could say, what's the probability that x is greater than 90? Now that seems really strange that that's even possible, because x could be anything, right? Like x is a random variable that could be from, I don't know, 0 to infinity. But I want to be able to now say, well, what's the probability that x is greater than 90 for all possible random variables with expectation 45? So maybe some binomial random variable, or maybe some geometric random variable. Like, it could be either of those, or any other random variable you want to make up that is a new distribution that you've invented. I can still tell you something about the probability that x is greater than 90. And that, to me, is a little surprising, just coming into this from the lectures we had before, because I don't know anything about that random variable. I don't know its variance. I don't know its distribution. I don't know where it goes. But I can still say something about this. It's not a very strong statement, but I can say something. Okay? And that will bring us to Markov's inequality. Okay, so a question for you. Let's say I have 100 students, and they take a midterm, and the mean on the midterm is 45. Can everybody have more than 45 on the midterm? No, they can't all be above average, right? Like if you did, then you'd average them and you get some number bigger than the average, right? So if you really want like kind of a silly little tiny proof, imagine everybody did slightly better than average. Everyone got 45.0001. Okay, well, you add all this up, divide by 100, you get 45.001. Doesn't work, okay? Here's another one. Let's say you want to know, is it possible that 50 people did better, or did greater than or equal to 2 times the mean, 90? This will be your first question. You might say, what happened to question A? I deleted it. It wasn't a good enough question. Okay, so is this possible?
For the purpose of this pi experiment, can you get a negative score?
No negative scores allowed. Good question. You could get a 0. That's allowed. Okay. One more time. Okay, so it turns out this is possible. And the way it could happen is, let's say you take all the small scoring students and you set them to 0. So you give 50 students a 0, and then all the large outcomes to 90. In that case, the other 50 students, the 50 students who don't have get a 0, they'd have a 90, they'd have 2 times the mean. And so overall, then the average would be 50 times 0 plus 50 times 90, which is 45. Okay? Make sense? You can kind of see that you couldn't go any further than that. But I'm going to give you a slightly different question. Any questions about this? Okay, related question. Actually, also I know the 50 students can't all earn a score greater than 90, but they can all earn a score equal to 90. Okay. All right, another one. Imagine we have N people, however many that might be, and let's say their average bank account balance is $5,000. What's the maximum possible fraction who have $15,000 in their account?
Yes or no?
No negative balances. Yes or no is not a good answer. One sec. That's supposed to be a short answer. Yes or no. Okay, it's fixed. Try redoing it again. Yes or no. I got a no vote. Okay, so the maximum number would be n over 3, the maximum possible fraction be 1/3. Because the idea is we could have the situation where 2/3 of the people have $0 and 1/3 of the people have $15,000 each, and that will yield an average of 5,000. Yeah.
What if people can have negative?
Yeah, right. No negative balances. Yeah.
Like, in that example,
In that case, I can no longer say this. Yeah, right.
like say someone owes, everyone else a whole lot of
Right. So if you're overdrafted, then that question is not the question I asked. So then you'd have a different answer. But in this world, where everyone has to have at least $0, our bank doesn't overdraft. That's how it goes. Okay. And similar but related question. There's no submission for this one. Let's consider a non-negative random variable where the expected value of x is 5,000. And let's say p is the probability that x is greater than or equal to 15,000. What's the largest possible value for p? Okay, obviously, it's related to that last question closely. So let me think about that for a second. Okay, what do you think? 1/3, yeah. Now, this could feel a little fuzzy because it feels a little different. The other one was about like a number of people, and this one's like some random variable. And this is where the notion of really understanding that a random variable maps from a sample space to a real number is helpful for understanding exactly why this is, okay? So again, I have some sample space of people, and what the random variable does is it takes that person and tells you some real number. So the connection between the previous problem and this more formal problem is to say that for all of the people who had no money, the random variable assigns 0. So I pick you out of a hat. Hey, you're someone who had $0. I pick you out of a hat. You're someone who had $0. Or more in general, right? Like for a random variable, there's a bunch of outcomes, and each of those outcomes goes with a number. Okay, and the expected value of x is just going to be, you do the weighted sum of the probability of each of the outcomes times x for that outcome. So all these get to be 0. All these get to be 15,000 after they get mapped out of the underlying sample space. And so as a result, the probability p is less than or equal to 1/3. Okay? All right. And so if I take this and I simply replace 5,000 and 15,000 with mu, that's the expected value, and I replace 15,000 with c, then I'm just going to have that fraction, mu over c. So 5,000 over 15,000 was 1/3. Here I have mu over c. That gives us Markov's inequality. Okay, so this is Markov's inequality. The probability that a random variable is greater than or equal to c is less than or equal to the expectation over c. And intuition is simply, okay, well, in the most extreme case, you would have a bunch of zeros and c's, and this kind of gives you like how you could possibly achieve that goal in the most extreme case. And you could never, for example, have 51 students with twice the midterm score out of 100 students. That would violate this rule. But really, I think this is the simple picture that gets you feeling comfortable with this, hopefully. Okay. The proof from the notes is a little different. I mean, this is the intuitive proof to me. I feel good about this. That line of reasoning feels good. But if you want, you could do a more formal notation, which if you want to prove Markov's inequality, not in terms of this kind of like example and then let's generalize the variable, we can instead do the following. We can use the mega-verbose form of expectation, which is that the expectation is you take each sample, each person, so to speak, and you map them to their bank account balance, and then you say the probability of getting that person. I was doing uniform before, but this lets you generalize beyond uniform. And that's the true expectation, okay? Then what you do is you say, you know what, this expectation is going to be greater than the following. Why? Well, what this expression here is it's saying, let's not add up everybody. Let's only add up everybody where x omega is greater than or equal to c. Okay, so I'm going to take all the small outcomes and put them to 0, just like you did when you were trying to imagine, how do I get half the people to have twice the mean? Okay, well, I'm going to take half the people and I'm going to set them to 0. Those are all the small outcomes. I'm going to force them to 0. And then what I'm going to do is the next part where you said, okay, half the people are now going to have that highest possible score, which was twice the mean, that was 90. We're going to give them the score c. So instead of having x omega, they're going to have c instead. Okay, so it's like 2 sleights of hand here. Okay, and I will note that this proof is a lot harder to follow than the argument before. But basically that part where you set everybody's mid-score to 0, like half of the students, that's this right here where you're adding up only the small, or where you're setting some of the small outcomes, some of the outcomes to 0. Okay, so I was adding up everybody. Now I'm adding up only the big ones. Okay, and what are the big ones? Well, I'm going to take this and replace it with the big quantity. Okay, so I know this is hard to follow in the middle of lecture, but it's the same idea, and it's a little tricky to understand precisely why this maps to the little thing we did before. Yeah. The expected value, why? Here, though, like the expectations, all of them. So if we're not adding up any of the ones that were, the true expectation is bigger than if we zero some of them out. Yeah. And then eventually, then I could just pull out this c, right? Because this doesn't have any dependence on omega. And so what that tells us, the expected value of x is greater than or equal to c times this right here. What is this? So this is adding up the probabilities of all of these omegas. So if I ever add up all the probabilities of some set of omegas, what is that? It's the probability of something. Not the whole sample space. It's only these ones. It's a subset of the sample space. An event. And what event specifically? It's the event that x is greater than or equal to c, right? That's what it says, right? So this right here is the event, the probability of the event that x is greater than or equal to c. And so that's expected value of x equals c times p of x greater than or equal to c. If you divide both sides by c, you get Markov's inequality. Okay? So this is an alternate proof. I don't think it's very intuitive. I think it's pretty hard to follow. Maybe it's good for you. The alternate proof, I think, is not quite as formal, but they're the same idea. The old one, and again, it does take some thinking to figure out exactly why they map to each other. But I think the really tricky thing, I want to repeat this about this proof, is that the part where we set some people to 0 is the adding up only some of the sample points. And the part where we replace the high-scoring students with the number we're looking for, in the most extreme case, c, that's this step here, where I go from x omega to c. Okay. I know that's a little informal, but somehow the intuition works well for me. Let's try and use this thing, Markov's inequality. Let's say we flip a coin n times, and x is the number of heads. What does Markov's inequality tell us about the probability that 3/4 of our flips are heads? Okay, so try and work on that. I'll give you like a minute or two on this one. Okay. So it turns out there's an expression you can come up with. I'll sit in the relaxing chair for a minute. And I'll do it on a piece of paper. You may not have paper, so good luck doing it in your head. All right. So first you need to figure out the expected value of x. It's a fair coin. You're flipping it n times. Okay. See how you were doing on it. Okay, I'll walk through the math. So, what's the expected value of x? N over 2. Great. And what's c? 3/4 n. So I'm just going to substitute those things in. So expected value of x is n over 2, or 0.5 n. I don't know why I wrote it that way. And so the probability that x is greater than or equal to 3/4 n, I'm just going to substitute this constant c. That's 3/4 n in the bottom. And then on the top I have 0.5 n. Okay, if I divide out that, we get 2/3. Okay. All right. So what this Markov's inequality tells me is if I flip a coin 1,000 times, the chance that I get 750 or more heads is less than or equal to 2/3, or whatever. Okay, whatever n you want. Is this bound good? Tight? I don't know. This is like informal, but what do you think? I heard a loud no, so you can adopt the answer or not. So if you flip a coin 1,000,000 times, what's the chance you get 750,000 of those heads? Is it like 2/3-ish, or is it lower? Okay, it turns out it is not a tight bound. The example I have on the slide is you flip a coin 1,000 times, the chance of getting 750 heads or more is less than 2/3, is what Markov's inequality. But the actual chance, assuming I didn't mess this up, the chances is wrong, is 6.74 times 10 to the minus 57% chance. Pretty unlikely, right? And if you think about it, I flip a coin, if I'm getting 3/4 heads, that's weird, right? Like if I have a fair coin and I happen to just get 3/4 heads, it would be crazy. Much, much, much less likely than 2/3. And actually, you'll notice there isn't even a dependence here on n. Okay? So if I flip a coin 10 times, Markov's inequality, a very loose bound, says, oh, it's a 2/3 chance you get, 8 or more heads. If it's 1,000,000,000 coins, 2/3 chance you get 3/4 heads. And that's not how reality works, right? As you have more and more coin flips, we expect that the probability is going to go down, that you're going to get some 75% heads, but Markov's inequality does not capture that. So it's a loose bound, but it is a correct bound. Okay, so it's very loose. It's always less than or equal to 2/3, but as n gets big, this bound gets increasingly useless. Any questions about that? Maybe a natural question, why are we learning this if it's so useless? Well, it's a stepping stone to Chebyshev's inequality. So it's a very, very easy to derive bound that once you have it, will let you do something better. Okay? So just like the union bound earlier, which let us estimate the probability of unions of events by ignoring all of the intersections of those events, you get an estimate of, you get a bound on a probability, and it may be pretty loose. In this case, it's extremely loose, right? 3/4 is, 66.66% is very far off from 6.74 times 10 to the minus 57%. I do note that it's possible to contrive a situation where it is a tight bound. I'm not going to actually say this out loud, but it's there on the slide for you if you want. But in general, for random variables, Markov's not going to be very tight. Okay. Earlier we asked, what happens if we drop non-negativity? What happens? Well, Markov's inequality as stated is no longer true. So for example, in a midterm, you have a minus 1,000,000. It was very bad. You had a bad day. I don't know what happened. It's possible for everybody else to do twice the mean because you drag the mean down to something quite small. There is a generalized version of this that works even if x is negative. I'm not going to cover it in lecture because it is not useful for getting us to Chebyshev's inequality, which is what we actually care about. But if you want, that's a little cul-de-sac that you can chase. Okay? All right, any questions about this as we proceed? All right, great. All right, let's talk about Chebyshev's inequality. This is where we're going to gain a new superpower. That's sort of the next step as we move on to fancier concentration inequalities. So let's look at this distribution below for some arbitrary random variable. Here I'm showing the count of the number of times that some particular I happens. So like the chance of getting 9 is going to be 0.05 and so forth. And we can think of visually of the expectation as the center of mass of this distribution, and the mass of any particular value like 17, it's going to be equal to the height of the respective bar. So these are going to be pulling, less, but it's further over. And that's one way to interpret the expectation. Okay? What Markov's inequality does is it gives us a bound on how much mass there could be above some constant c. So for example, if c equals 2 times the expected value of x, it tells you how much of the possible mass could be over here. That's what the expectation, or what it was all about, right? So that's the amount you could have over here. Chebyshev's inequality is going to be different. It's going to say, all these little scribbles I put, it's going to tell you how much mass lies outside of a certain range, right? So how far could we deviate from the mean in general? Right, and that's important if we think about that estimating the coin flip, or probability of heads rather. So we flip a coin a bunch of times. The p hat we came up with, this estimate, it's the average of our coin flips. So then the question is, how far could that average have deviated from the true p? That's what we want to know. So there's some underlying process that we want to model here. And we want to know, okay, so at some point if we make some measurement, how far could we be off from the beginning? And that obviously has a lot of applications, like I'm building, I don't know, some electrical grid thing, and I want to know what's the probability the voltage ranges outside of some normal, like nice nominal value. This could be useful in such a case, right? So this is going to give us a very crude bound. If we don't know really anything about x, it's going to give us almost anything about x. It'll give us a crude bound on how likely it is that we stray outside of this range. That's the intuition. Okay? Now, unlike Markov's inequality, which uses only expectation, Chebyshev's inequality is also going to use the variance, and it's going to give us a sense of how far we can go from the mean. Okay? So how it's going to work, the Chebyshev's inequality, which I'll prove in a moment, but I'm just going to state it first. If x is a random variable with some mean, then for any constant c greater than 0, we have the following statement. Okay? What does that statement say? It says that the probability that x minus the mean is ever bigger than c. Okay, so how much of the mass is that far away from c? It's more than c units away from the mean, is always going to be less than or equal to the variance of x over c squared. Okay? I didn't tell you where that came from yet. We will. But first I want to build some intuition for what it means. So again, I'm going to prove it downstream, but first let's say what it means. Okay. So there's another way to, I think this is the most intuitive way and most interesting thing about Chebyshev's bound is, let's pick a very specific constant. That's going to be in terms of the standard deviation. Okay, so let's suppose I want to know c equals k sigma. Okay, what is the upper bound? So just do some math for me for a moment. Imagine that the constant I pick is k times the standard deviation of x. Okay, what's the upper bound going to be that we get here? So what's the question mark? And then the next question is going to be interpret that for me. But for now, I just want you to do the algebra. Uh-oh, is it not the right question? That's not, is it? I knew that was going to happen. Okay, don't answer the question on there because it's the same one from before. Not sure how that happened, sorry. Okay, so do the algebra, but don't actually submit anything. I'll sit down and do it too. So the variance is sigma squared. That's the key fact you need to know. Okay. So if I plug in the sigma squared for the variance, then I'm going to get, So I plug in k sigma at the bottom, I get k squared sigma squared. Happy with that? Because that's just what I said c is. And if I plug in sigma squared up here, I get sigma squared over k squared sigma squared. So I get 1 over k squared. Okay? All right, so why do we just do that? Well, what I'm telling you is that the probability that x deviates from the mean by more than k sigma is less than or equal to 1 over k squared. What does that really mean? Okay, so let's see. This one I feel probably good about, but now I'm a little nervous. Let's see. Okay, yeah, all right, there we go. So suppose we have a random variable. What bound can we place, like any random variable at all, as long as it has finite variance, what bound can we place on the probability that we're more than 3 standard deviations from the mean and more than 1 standard deviation from the mean? And I'm going to sit in the thinking chair and let you stew on what this is even going on for about a minute and a half. Feel free to chat with your neighbor. Okay. It tells us that if we plug in 3, right? So remember that we want to talk about what happens. Like, what's the chance that we're 3 standard deviations from the mean? I would be plugging in 3 sigma here. 3 sigma gives me 1 over 3 squared, or 9. And what that tells us is that for any random variable in the universe, there's a less than 11.11% chance that you could be 3 standard deviations from the mean. For the 1 standard deviation case, it doesn't tell you anything. It says that the chance that you are less than or equal to 1 standard deviation from the, or sorry, greater than or equal to 1 standard deviation from the mean is less than 100%. So it tells you nothing about 1 standard deviation, but it does tell you something about the 3 case. So just to reiterate, though, what's going on here, I don't care what grade scope you ever go to. You will never, ever, ever find a distribution where more than 11.11% of people got 3 standard deviations from the mean. It's literally impossible. That's what this says. And that's true for any random variable. I don't care how clever you try to make it, as long as the variance is finite. And we've not talked about what it could mean for a variance to not be finite, and we never will. But that means that that's as high as it could go. I think that's kind of a profound statement, right? Yeah.
But by Chebyshev's inequality, it is still technically possible for 200% of the class to get, no, not 200, it's still possible for 100% of the class to be more than 1 standard deviation.
Right, so Chebyshev's inequality is loose. It says that it's possible, with this upper bound for probabilities, for 100% of people to be more than a standard deviation above the mean. Not a very useful statement. You know that, right? Like, the actual probability is much lower. Right. Okay, great. All right. Now, I should note that Chebyshev is a loose bound, and I want to acknowledge something you might have seen that's similar before, which is the 99.7 rule. You might have heard this before, that, oh, well, when I take exams, I thought the probability that I'm less than 3 standard deviations from the mean is like 99.7 or something like that. Or the chance that I'm more than would be 0.3% equivalently. So that is not what we just showed. We had a much different, looser bound. It said the probability of being more than 3 standard deviations is 11.11111%. And this other thing said 0.3%. I mean, who's seen this thing before, the 0.3%? Yeah. So what's the difference? Well, Chebyshev's works for any distribution in the universe, and this only works for a specific distribution called the normal distribution. Okay, so Chebyshev is true for every distribution. This is only the normal distribution, which we'll talk about next Tuesday, in which I suspect not many of you will be here. In fact, there's actually a chance that I might have to do that lecture online, because my wife's mom broke her shoulder, so we might be going to Chicago to help out. So I'll let you know. Anyway, all right. Okay. So Chebyshev's inequality gives us a sense of how far a random variable can possibly stray from its mean. We had this just as an example of a fact it tells you. It says no more than 11.1111% could be more than 3 standard deviations away from the mean of the mass of the distribution. So where does that come from? How do we get this? Well, it turns out that it's a fairly straightforward consequence of Markov's inequality with one little clever trick. Okay? So the first thing I'm going to do is I'm going to show you a bad proof where we're going to get stuck. And I'm going to say, okay, well, x minus mu, absolute value, is a random variable, right? It's a function of a random variable, so it's also a random variable. And then I could try to say, well, okay, like we already know how to find the Markov's inequality tells us how to find the probability that x is greater than or equal to c. We just need to know expectation of x. That's what Markov's inequality is. It's that Markov's inequality tells it would be less than or equal to the expectation of x divided by c. But that's not going to work for us. I should also note that x minus mu is definitely non-negative, so it definitely applies to Markov's inequality. But the problem is when I try to compute the expectation of x minus mu, I get stuck because I can't really take the expectation of an absolute value very nicely. So what I'm going to do instead is be very clever, and I'm going to again observe that it's a random variable, but now instead of thinking about x minus mu absolute value, I'm going to observe that for every omega, for which x of omega minus mu is greater than or equal to c, we also have that x of omega minus mu squared is greater than or equal to c squared. In other words, these two probabilities are the same. Okay, so these two conditions, if one is true, the other is always true. So the absolute value of a, if you know the absolute value of a is greater than or equal to b, then a squared is always going to be greater than or equal to b squared, as long as b is non-negative. How do we know that this thing's non-negative? Better.
We're the ones who choose.
Yeah, we're choosing it. Yeah, exactly. So there you go. Yeah, and what I just said is not totally obvious, that it needs to be non-negative, but if you sit down and like work it out on paper and you think, is it true that absolute value of a greater than or equal to b reverse implies a squared greater than b squared for positive b or non-negative b, then it's a separate little proof hidden, but hopefully it seems plausible here. These two conditions are equivalent. Okay? If those two conditions are equivalent, then I can actually compute this probability, and it'll act as since it's equal to this is a proxy, an exact proxy. So we're going to use this instead. Okay? So I'll say, okay, well, instead of considering the random variable x minus mu absolute value, I'm going to consider x minus mu squared. And now all I got to do is I can apply Markov's inequality with no trouble, because I can compute the expectation of that. Okay? What Markov's inequality will tell us is that the probability that y is greater than or equal to c squared is less than or equal to expected value of y over c squared. Why is this true? That is literally Markov's inequality. There's nothing special there. So now we just need to know what is y, or expected value of y. So what is the expected value of y? I guess I'll give you a shorter amount of time. I'm gonna wait for some responses. Here's what I call a pacing question. I just don't want to talk too fast. Okay, so the expectation of this right here, by definition, this is just the variance of x. Like, that's how we define variance of x. So in other words, the probability that y is greater than or equal to c squared is going to be less than or equal to the variance of x divided by c squared. And since this red probability is the same as this black probability, we'll be in good shape. Okay? All right. So that's the whole thing. We proved Chebyshev's inequality. It's like a pretty small amount of gymnastics. We just make up a new random variable, x minus mu, and at squared, and we compute its expectation, which is just the variance, and we apply Markov's inequality. So if I compare these two things, this is the two different inequalities we've shown so far. Markov's inequality says the probability that a random variable is greater than or equal to c is just the mean divided by c. Okay? And that gives you the probability that the random variable exceeds some value. It's a very loose bound. And the condition is that the random variable is non-negative, and it requires you to be able to compute the mean, naturally. Okay? Chebyshev's inequality is a little different, right? It's this expression here. It says that the probability that a random variable minus its mean, absolute value, is greater than or equal to c. So how far do you go away from the mean? It's always going to be less than the variance of x over c squared. And an example we showed is if you plug in a c, which is equal to 3 times the standard deviation, then this is going to be 11.11%. This is a relatively tighter bound, but it's still pretty loose. As we observed, you brought up the silly fact that it shows that a tautological fact about the chance of being within more than a standard deviation away. And the condition here is that the variance x is finite, which is a minor technical condition, not really part of our class. And in this case, it requires you to be able to compute the variance of x. Okay? All right. A lot to digest, but that's what homework's for. Okay? So even though Markov's inequality is weak as a way to understand x, we were able to enhance its power by just making up a new random variable, which is x minus the mean, squaring that, computing the expectation, and then apply Markov's inequality, which requires us to compute this expectation. Okay? And since the expectation of that new random variable is just the variance, then that bound is in terms of the variance. It all works out very nicely. So whoever discovered this, probably a couple hundred years ago, I don't know, something like that, probably felt like, oh, that's pretty cool. Like, I feel like I got something for free here. I got a tighter bound by just playing this little game. Yeah. So I'm being a little vague here, but an example would be that the Markov bound, the probability I get from the true probability is can be quite far away. Like, for example, 66% chance that you get 3/4 heads being much bigger than 10 times 10 to the minus 57th or whatever. And in general, these bounds are going to be a little tighter, but in a more technical class, we would talk more about precisely what we mean. Okay? And I'll show you an example of the bound being tighter for Chebyshevs. So these are not super technical terms. Now you might ask yourself, could we do this again? Like, what if we make up a new random variable like x minus mu to the 10th? Could that be helpful? Like, if I knew that somehow for a binomial random variable, could I get an even tighter bound of some kind? And the answer is indeed yes. With a little bit of caveats. But if you go, if you consider all those different random variables, if you make up more of these, you play another game where I consider x minus mu to the 3rd, x minus mu to the 4th, and so forth. If I take the expectation of all of those different things, I can combine them to form an even nicer bound. And that'll be on the homework, actually. I'll go play around with that, and you'll derive something that's a fancier bound. I'll note just briefly, it's beyond the scope of 70, but this specific quantity, the expectation of x minus mu to the I, is called the ith moment. So the mean will be the first moment, the variance will be the second moment, and so forth. And if you somehow have all of those moments off to infinity, you can derive an even tighter and quite good bound that I won't tell you about today, because that's on the homework. Right. So basically, this trick of going from Markov to Chebyshev by creating a new random variable, it's a nice, clever trick. A little hard to digest, but the homework gives you a chance to digest it all the way to infinity. All right. Yeah. Yeah, apply Markov's inequality on the new variable, on y. That is Chebyshev's inequality, yeah.
Oh, okay, so that's
Yeah, Chebyshev's inequality is Markov's inequality applied to this new random variable. And so then the natural question is like, is there like Chebyshev plus, where you take the third moment? And yes. And you can keep going to infinity, and then you get the Chernoff bound. All right. All right, let's talk about a bad use of Chebyshev's inequality that's not as super interesting. But I want to use this to compare. So you asked that question, what do we mean by loose versus very loose? I'm going to give you an example here showing you why this is relatively tighter. Okay. So earlier we tried to use Markov's inequality to understand the behavior of x binomial where we flip a coin n times and it's fair. And we wanted to know what's the chance that 3/4 of our flips are heads. Now using Markov's inequality, we found that quantity is, we could bound it by 2/3, but that's a really bad bound. Okay? In real life, as we flip more coins, the chance of getting 3/4 heads should drop. And what we'll see is if we use Chebyshev's inequality, we get that property, that we'll see a dependence on n. Okay? Not the right dependence, but at least something. So here's the idea. Let's suppose we want to use Chebyshev's inequality to compute the probability that x is greater than or equal to 3/4 n. This is Chebyshev's inequality. I've put the left in blue and the right in red. Doesn't really matter, but that's what we usually use. Okay? So first we're going to write out the expectation and variance of this random variable. So the expected value, as we did before, of a binomial where we flip in coins that are half heads will be n over 2. And then the variance, which is from an earlier lecture, will be n times p times 1 minus p. For a fair coin, that's 1/4, or sorry, 1/2 times 1 minus 1/2, so that's 1/4 times n is 1/4. And so now, if we want to apply the Chebyshev bound, we have to take this right here, and we need to do a little bit of gymnastics to make it look like the equation on top, the blue one. Okay, we already know how to use Markov bounds directly with this. If we want to use Chebyshev bound, we have to turn this and turn it into a statement that is relative to its mean. This is not a statement about x being how far away from its mean. So what we're going to do is we're going to subtract the mean on both sides. So the probability of x greater than or equal to 3/4 n is, of course, the probability that x minus the mean is greater than 3/4 n minus the mean. And then what I'm going to do is, what's the mean? It's n over 2. So I'm going to plug in n over 2 here, and I get n over 4. So all I've done here is taken this right here and turned it to n over 4. And we're pretty close. But here's a question. What's the relationship between what we have here, the probability that that x minus mu is greater than or equal to n over 4, and the absolute value of x minus mu is greater than or equal to n over 4. Yeah?
The one with the absolute value is double that of non-absolute value.
No, this one's bigger at least. Can be bigger. It's not necessarily double, because we don't know what x's mass is. But basically, there's some samples who may be, once we take this absolute value, that they're going to get included here, where they weren't included on the right. Okay? So the probability that the absolute value one's going to be bigger. You said double, but that's only true if it were symmetric around the mean. And let me just check my battery, shall we? Oh, we're in great shape, 18%. I feel good about that. Okay. Okay. My cord didn't reach, so it goes. All right, so what we just showed is that this probability here, x greater than or equal to 3/4 n, is equal to probability of x minus mu is greater than or equal to n over 4. This right here is less than or equal to the blue expression. Okay, so that's the blue expression. And so what about this blue expression? What's that going to be? Now we can apply Chebyshev. So we can't apply Chebyshev directly to this right here. So we transformed it into this first. And then it doesn't matter. We're just trying to compute an upper bound. So this is less than or equal to this blue equation. And is this one in the right form? Yeah, it's like a statement about how far you are from your mean. Okay. So now we just apply Chebyshev's inequality. Okay, what do I do? Well, I'm going to need to know the variance of x, and I'm going to need to know c squared. So what's c squared? Or what's c, I guess? N over 4. Okay. So we're going to have here c squared. Oh, sorry, I guess I substituted in. Oh, no, okay, that's the whole thing. So this is the red equation. So yeah, what's c squared? It's n over 4 squared. And what's the variance of x? N over 4. So n over 4 over n over 4 squared is 4 over n. Okay? So what I've just showed is that for a binomial random variable, the chance of getting 3/4 heads is going to be less than or equal to 4n. Okay? So what this tells you, for example, in an election where the chance of voting for a candidate is p equals 0.5, the Chebyshev bound says the chance of getting 75% of the vote is less than 0.04% if 1,000 people vote. But I should note that this is a pretty silly, not all I did is I plugged in the numbers there, but this is a silly use of the Chebyshev bound because we already know how to compute this chance exactly. And it's a lot smaller than 0.04%, right? Like it's a much, much, much smaller number, like 10 to the minus 57. So this isn't really the ideal use, but I do want to note that it's better than the Markov bound. The Markov bound was just a constant, which doesn't make sense really. I mean, it's true, but it's not useful. And in here, we use the Chebyshev, we get a tighter bound, something where as you flip more coins, the probability goes down, but it's still a very, very loose bound. Okay. All right, now we get to probably the most interesting part, which is using the Chebyshev estimate not to compute the chance of getting some number of heads, but to compute the chance of getting heads on the coin in the first place. Like we want to compute p itself. So we want to flip some coins and figure out what's p. So to note before, this example is we already know p and we want to know what's the chance of some number of heads. Now we're going the other way. We have the number of heads, we want to know p. And this is something that we could do uniquely only because we have Chebyshev. This old problem we had up here, we could do this using the distribution for a binomial random variable and summing up the probability of a bunch of events. This one we have to use Chebyshev and be a little more clever. Okay. Give you a moment to look at this for a sec. So we have a coin, which comes up heads some probability p. We toss the coin n times, and let's say x is the number of heads, and it's just the sum of each of these Bernoulli trials. Our empirical mean is just going to be x over n, where x is the sum of all those separate flips. And the question is, how big does the n need to be so that the probability that we are epsilon away from the true p is greater than or equal to some confidence interval? Okay, that's what we want to try and do. Now that feels like a slight mismatch to what we were doing with Chebyshev, right, which is this less than or equal to thing. So we're going to do a little bit of work here, but that's our goal. Like that was our original goal. We want to know how many times do we need to flip this coin so that we're less than or equal to epsilon away with confidence c. Okay, we already did the first transformation. Actually, first I'm going to tell you where we're going to go. So I want to turn this expression here, which hopefully is intuitive. The probability that our estimate is less than or equal to epsilon away from the true p. We want that chance of that being, like our experiment coming out good, to be at least c. It turns out that I can also frame it as follows. I want the probability of a bad thing to be less than or equal to delta. The chance that our estimate is greater than or equal to, the chance that our estimate is more than epsilon away from p is less than or equal to delta. So I'm going to take this up here and turn it into this reverse form because this one's amenable to Chebyshev's inequality. Okay. A little boring. In fact, not even mentioned in the notes ever, but I'm going to do it. God help us. Okay. But I'm going to show you that this thing up here, hopefully it feels intuitive, and this is going to be, I'm going to show you that this is the same. Any questions about what I'm trying to do? Like why this is where I'm starting or why this is where I'm trying to get to? So again, to reiterate, the most important part is up here. We want the probability of some good thing to be greater than or equal to c, which is the same thing as the probability of some bad thing to be less than or equal to delta. So what was the relationship between c and delta? Well, the idea was delta and c were just 1 minus each other. So we know that c equals 1 minus delta. So the boring thing I'll do first is I'll just say, first, this is 1 minus delta. Okay? And here we go. There's me trying to mess with the Windows formatting and making the Mac formatting bad. Sorry. Okay? So how big does n need to be so that we have now at least a 1 minus delta chance of being within epsilon of the true p? That's what this means. Okay. The next thing I'm going to observe is that the probability that this good thing happens, being greater than or equal to 1 minus delta, is the same thing as the probability that this bad thing happens is less than or equal to delta. Okay? Why is that? Okay, well, on the left, this blue thing this says there's a, let's say we have a 1 minus delta chance of being within epsilon of the true value p. That's the same thing as saying there's a delta chance of being more than epsilon away from the true value. Okay, does that make sense? At least plausibly? So these two things are equivalent. Okay? All right? So basically what we're trying to ask is how big does n need to be so that the probability of the bad thing is less than or equal to delta? Okay? The last little annoying step is that Chebyshev's inequality is a greater than or equal to statement, and we have a greater than statement. Okay, well, it's actually not a problem at all because we can say that the, oops, there's a missing sign here. Okay, let's see. So the probability is less equal. So we could say that the probability, where I'm at, such that, because the probability here is less than. Okay, I'm regretting this one a little bit. This transformation that gets skipped in the notes. But basically, the probability that, so we've shown, if you're following me, maybe I've lost you a little, that the probability that, like this is what we want, but it's just good enough to find a bound on this other quantity because the one we're looking for is less than or equal to this one. Okay. If you didn't like that, all right, the basic version, I know that was probably hard to follow. I'm sorry, I apologize. You have to have questions in that one, otherwise it's just like random algebra. But this expression up here, hopefully you feel good about that. And if you didn't follow my argument, you're going to have to trust me that it's equivalent to finding this probability. Okay? We can reframe it as finding this probability. Okay. All right. So if I lost you there, what I do want you to think about is if you just trust me that these two things, that the n that satisfies this also satisfies this one, now let's try and do that. So I want to try and bound the probability of the bad thing happening using Chebyshev's inequality. Okay? Why is this thing bad, actually? Question for you. Why am I saying this is bad? Yeah?
Means that we're off than what we budgeted by.
Yeah, we're off more.
The election case would mean we totally blew it.
Right, we blew it. We went beyond our epsilon. So what's the chance that we went beyond our goal? Okay, well, let's do some algebra. Okay, what's the expected value of our estimate? This is homework 11 problem 4a. Like if we look at the expectation, if we actually do this process, the expectation is going to be p. So on average, we're going to be right. Okay, I do a polling, I'm going to be right. Sometimes I will, if I were to run the experiment an infinite number of times, I'm going to get p exactly right. But that's not how it happened. I'm only doing the experiment one time. I'm only going to ask n people. Okay, so if the expected value of p hat is p, we could say the following. We can say, of course, that p hat minus the expected value of p hat. So this right here is just showing you that this is really in the Chebyshev form. We are really talking about a statement about our deviation from our mean. And because of that, we know that it's going to be, that this probability is going to be less than or equal to the variance of our p hat. So p hat is what we came up with, and we want to know what's the variance of this random variable. And again, hopefully homework 11 primed you to be able to do this, follow this during lecture. So we just need to know the variance of p hat. What's the variance of p hat? Well, it's going to be the variance of x over n. Okay? What's x? Number of heads, which is the sum of these different random variables. Okay. Oh, first I pulled out the n. Okay, that's just a property because n's a constant. So if I take the variance of all these, can I separate out these variances? Can I just rewrite this as the sum of the variances? Yes, why? Coin flips are independent, so it's n times the variance, which gives me just n over n squared. And then the variance of a single coin flip is p times 1 minus p. Okay? So we divide out those n's and we get p times 1 minus p over n. This is like that lecture we did all that stuff, which was like 1 plus 1 equals 2. So we've done a ton of work in order to show that the probability that our estimate is off by more than epsilon is equal to p times 1 minus p over n. Okay? So that's what we've shown here. All right. Now, if I, let's see. Okay. So that's the variance of p hat. Okay, so we have the variance of p hat, p times 1 minus p over n. And so now if we want to actually use Chebyshev's inequality, we need to substitute in the variance on top. And that's going to be p times 1 minus p over n. And then where did this epsilon squared come from? Chebyshev's inequality. It's the variance divided by this quantity squared. Okay? So we're almost there. Now at this point it might seem weird. The variance of our estimate is a function of p, the thing we're trying to estimate. Like, that's weird. Like, how the hell would I know that? Like, p is what I'm trying to find. So I feel stuck. How could I possibly fix this? I mean, if I knew the real p, I guess I'm done, but then I don't. Yeah? Yes, perfect. We can bound this above. I like that a lot. So this is my last question for you guys, which is, okay, well, I'm just going to replace this thing. I'm going to replace p times 1 minus p with its maximum possible value. And that'll be a suitable upper bound. And let's hope this question works. Okay, I have to complete the action using, oh, it didn't work. All right, never mind. Okay. Okay, you have to think about it. That's a strange one. Don't scan it. You're going to get an error from Google. Okay. Okay, what's the biggest possible value for p times 1 minus p? 1/4. How would that happen?
P is 1/2.
Yeah.
1 minus P is 1/2.
Yeah, p is 1/2. 1 minus p is 1/2. That's as big as it can get. And so that's where that 1/4 came from earlier. So the probability that the bad thing happens is less than or equal to p times 1 minus p over n times epsilon squared, where epsilon is our desired accuracy, n is the number of coin flips, and p is the real answer. So the variance of p hat depends on the real answer of p, but we don't know p. So what we could do is say, oh, well, this thing is going to be less than or equal to 1/4. It's a cool trick. Okay, so you get painted into a corner because your answer depends on the thing you're trying to find. But they could say, well, okay, I'm bounding above. It's never going to be more than 1/4, so we get 1/4 in epsilon squared. Okay? All right. Now this makes some sense, right? Like the fact that it depends on p, it makes sense. Why? Like what would be the most extreme case? Like pick a p where your variance, where this probability is going to be very low. Yeah, 0. So if the coin always comes up 0, the variance is going to be 0. This whole thing will be 0. We're going to be always exactly right. So this expression is going to work for all possible p's, but if your p's lower, then it's an overestimate, and that's fine. Okay? So what we've just shown is that the probability of the bad thing happening is less than or equal to 4n epsilon squared, with a lot of thinking. Okay? Now remember, we want an n such that this whole thing, the probability of the bad thing happening, is less than or equal to delta. So to achieve this goal, we're just going to multiply both sides by n and divide both sides by delta, and we get this expression. Okay, so that was quite a technical and long journey to get us to this number. So we did like an hour and 10 minutes of straight talking. We derived Markov's inequality, Chebyshev's inequality. We proved that they were correct. We mapped this coin flipping problem onto Chebyshev's inequality and got this expression. It's quite a lot to digest. Okay. All right, but this n, what this tells us is that the whole thing we did at the beginning, where we get this whole family of statements about the quality of our estimate of p, are all true, and this is our proof for it. Okay. Any questions about this? Yeah, this is like probably the longest narrative of the entire 70 class, except for the discrete math part where you go into encryption. Yeah. Yeah, how do we get from a good event to a bad event?
Yes.
Yeah, so let me just go back to that really quickly. So the basic argument here, which I don't think I have enough bandwidth to really go through it in detail, again, but the basic idea is this is what we wanted, and the key thing was this statement here. Like, this is the slide you want to look at again, that we can flip this sign here. Yeah. So think about it in terms of good event and bad event. I think that's the best way to think about it. Okay. All right. Okay. I want to touch on two more things. One is the weak law of large numbers, which is, I said this out loud earlier, that if you run the experiment long enough, you're going to be exactly right. The weak law of large numbers tells us that. Okay. So it's a bit of a detour, but the basic idea is, let's say we are trying to estimate some random variable's mean, and we want to know how close are we going to get in the long run. So I'm going to do a bunch of samples. I'm going to add them all up and divide by n. Again, just like homework 11, question 4. Okay. Let's say that these are all sampled from that true same distribution. So they're a bunch of IID random variables. They're independent, and they have the same distribution. And let's say the expectation of those random variables is mu. Let's say the variance is sigma squared, and it's a finite variance. And let's say we want to know what is the chance that we eventually get to some arbitrary level of precision. So I pick epsilon equals 0.0001. I want to know what's the probability that we're within 0.0001 of the real mean if we follow this process, and we just keep doing at more and more and more trials. So the weak law of large numbers says no matter how precise you're talking, I want to be within 10 to the minus 50th of the true p. If I keep sampling more and more and more and more times, dividing by n and then subtracting off the mean, that probability is going to go to 0. Okay? So how does this work? Okay, well, this is going to be very similar to the kind of math that we're doing today. It's not a Chebyshev thing, but it's going to be very similar. So in order to solve this question, I'm going to say sigma squared is the variance, okay, of this xi. Let's say Sn is just the sum, the numerator here. And then y of n is going to be Sn over n. So we could think of S5 as the sum of the first 5 terms or whatever. And as you add n bigger and bigger, you'll get more and more Sn's and Yn's. So if I want to solve this, if you're watching online, you can try and figure out the expectation of Yn and the variance of Yn. But these are the two quantities that we're going to need. Okay. So first, I'll say, what's the expectation of Yn? Okay, well, that's just going to be the expectation of this whole thing, this sum over n. Just as before, we're going to apply the expectation, linearity of expectation. It's going to be the sum of all the separate expectations. They're identically distributed with average mu. So we get mu n over n equals mu. Okay? And we'll see why this is useful in a sec. Again, this is the probability of this bad thing happening is 0 in the large n limit. And then what's the variance of y of n? Similar to before. So the variance of Yn is going to be, again, the variance of the sum of x's over n. Okay? We can pull the n squared out. We actually already did this in an earlier proof today. These variances, again, these are all just independent random variables, not necessarily coin flips. So we could say n times the variance xi. That leaves me with just sigma squared over n. Okay? So over here, then, the variance of Yn is sigma squared over n. The expectation of Yn is mu. And now we could do a Chebyshev problem. Now we do this, we can say that Chebyshev's inequality will tell us something here. We're recasting this whole thing in terms of how much this random variable here is deviating from its mean. Okay, so the probability that this new random variable, this estimate of the average, the probability that is farther than epsilon away from its mean is going to be less than or equal to the variance yn over epsilon squared. We know that for sure. And what we just did now was we computed this variance yn. What was it? It was sigma squared over n. Notice that this variance goes down as n gets bigger. So if I keep doing this over and over, this variance is going to go to 0. And if that variance goes to 0, this probability is going to go to 0. This upper bound on the probability. So whatever the real probability is, we're squeezing it until it's 0. And so the limit here goes to 0. So the intuitive picture here is just if you do a bunch of experiments over and over and over, the variance is going to shrink around the mean, and then eventually it'll go down to 0. Okay? All right. Any questions on this? You guys tired? Yeah. Yeah, okay. How many slides back? I'm going to do that one right after class. How about that? Do you have a minute after? Okay. All right, one last thing is talking about bounds beyond 70. So I'm going to talk about a couple little fun facts about the universe quickly that are a bit outside of the main scope of our class. One is confidence intervals. So we talked about this at the very beginning of class today. So we're trying to find the probability p that a coin comes up heads. You've tossed it a million times. You got heads 35% of the time. How confident are you that p equals 0.35? How confident are you that it lies in a certain range? So how confident are you that it is exactly 0.35? What do you think? 0, right. That didn't happen for sure. How confident is it in this range? Well, I can use that expression from earlier. We could say that delta is 1/4 n epsilon squared, where, say, epsilon's 0.05 and n's a million. Okay? This is called a confidence interval, and it's common in experimental science. You'll hear this idea of a 95% confidence interval, where we're saying, okay, what's the probability that the true thing I'm looking for is in this range? Is that probability is less than or equal to 0.95? I don't know why I put equals. Okay. All right. And that interval is going to be calculated based on some experiment like the one we did earlier. Yeah. All right. Coin flip bound tightness. I want to talk a little bit about homework 11, which is if you derive that extra super bound called the Chernoff bound, which you'll get to, you'll see you get an even stronger expression for epsilon and delta in terms of n. And this expression in particular, a little spoiler on the homework, is that the Chernoff bound tells you that if we have a specific epsilon and delta in mind, now the number of coin flips we need is only 1/2 epsilon squared times the natural logarithm of 2 over delta. So there's a different expression, like the delta comes cheaper here, right? It comes more, it's relatively more expensive, yeah. So the observation here is that confidence is cheap. That is if I just misspoke. Why? Okay, yeah, delta comes cheap. That is if I want to go from a 10% confidence to a 1% confidence, for example, I only need to go from 15,000 to 26,000 flips. But if I want more accuracy, that's going to be relatively expensive because it's not inside this natural logarithm. If I want to go from 0.01 to 0.001, I need more flips. I got to do, if I want to get, this, because this is a square, just getting this 10x better result requires 100x flips. All right. And then the last thing I want to talk about is polling in the real world. So the Chebyshev bound tells you a certain n. The Chernoff bound, which you'll derive on the homework, gives you an even tighter n. It'll tell you that if you want to know the election results to within 1% with 99% certainty, you only need 26,000 people, which is better than the Chebyshev bound, which we didn't show. But the reason this is hard in reality is that you need to get those 26,000 people to respond, and you need to ensure that person responds and person who votes for Donald Trump are independent. You have to have those things actually be, you really need them to be totally independent facts, and that's pretty much impossible to do. I will note that you can get an even tighter bound than this 26,000, where we can use a normal bound, but that's going to require us to take on a new, totally different adventure, like a different type of random variable. So what we're going to do starting Thursday is rather than having random variables that have a discrete domain, we'll have a continuous domain. So there'll be an infinite, but the random variables will now be continuous instead of discrete. All right, thank you, everybody, and hopefully that all made sense.